In today's video, we are going to review the atomic model. This is going to be a short answer question on the Unit 5 test, so you're going to want to make sure that you write this down. You're going to have to define the atomic model from Democritus to the quantum model, including dates and people. Okay, so let's go ahead and up at the top, you should all have your journals out. If you do not have your journals out, take your journals out or a separate sheet of paper so that you can write this down as we go. Okay, atomic model. Now, if I will post this video in the learning bundle for Unit 5, so if you need to go back and rewatch it again, you can go hear it. Okay, the first time we heard the term model, or excuse me, atom, was around 400 BC. All right, and that was Democritus. Democritus. Okay, we learned this back in Unit 3, and he said atom. He didn't really know what that meant, but he thought it meant a particle that you eventually could not split up. So we're just going to draw a little dot, and that's going to represent Democritus's atom. Okay? Now, we went a long time before we had an additional development, so to speak, in the atomic model. The next time that happened was 1897. Oops, 1890. Helps if I write the right dates down there. Okay, 1897. 1897, Thomson came along. And Thomson found the electron, right? That's what he did. He discovered the actual electron. He also found that's my little symbol for electron right there. He also found the charge to mass ratio of an electron, but he's credited for finding the electron. And what we eventually knew, but we didn't know where they were, was that you had an atom and that these electrons were randomly distributed. He didn't really have a pattern, but we just have them all spread out. And a lot of times this is what's referred to as the plum pudding model. Now, I realize for some of you, you have no idea what plum pudding even is. However, it's the name that goes with it, so I'm going to teach it to you. Plum pudding, kind of like chocolate chip ice cream, M&M ice cream, they're all spread out. There's no order to them. We knew we had this negatively charged particle, and it's all spread out. Which was great, except we still had some questions. The questions after Thomson included, where was the positive stuff, okay, and where was the rest of the mass? Because if you remember correctly, the electrons are very small. They're 1/1000th the size of a proton or a neutron. And so the questions after the Thomson model were where's the positive stuff and where's the rest of the mass in the atom? Well, along came a guy named Rutherford. And Rutherford came along in 1911, and his big contribution, okay, was that he found the nucleus. Okay, so he discovered the nucleus. So now we had Thomson's plum pudding model where they were all spread out. It didn't answer any questions about the electrons, but it did give us an extremely small positively charged center of the atom called a nucleus. And then we still had all of these random, these just represent negative signs, that's all I'm trying to do there. Okay, but we still didn't know where the electrons were, and that was the big question that was driving research after Rutherford was, where are these electrons? Where are they? Where do they exist? Etc., etc. So the next person to come along was Niels Bohr, and last names are just fine here. Okay, he came along in 1913, and if you remember, he looked at the hydrogen line emission spectrum, which was that fancy thing we looked at that had the purple and the turquoise lines we looked through our spectroscopes. And what Bohr did is Bohr came up with what's called the planetary model. Planetary, that should be an A, planetary model. Okay, and the reason we call it the planetary model is we still had the nucleus from Rutherford. Okay, Rutherford's atom model doesn't have a fancy name. Thomson was the plum pudding, Rutherford just found the nucleus. Now Bohr's model is called the planetary model because what you had was these situations where you had electrons orbiting the nucleus in these nice fixed paths. Okay, so remember we had the first main energy level, the second main energy level, and they were these, let me lower this down just a little bit, okay. The planetary model essentially stated that electrons circle the nucleus in certain, we're going to say 2D here, 2D quantized Now this whole quantized just means that there's only quantized paths. If we know nothing about a quantum, it's that it's a fixed amount of energy. So they only could exist in certain levels. You couldn't be in between n equals 1 and n equals 2. You were either in the n equals 1 level or in the n equals 2 level. That was it. Okay, so Bohr 1913, the planetary model, electrons circle the nucleus in certain 2D quantized paths. Okay, the 2D piece is big here. And this is the model that most of us, I think, are the most comfortable with. We also can sometimes call this the shell model, depending on your sources and depending on what they're looking at. Okay, and that worked, except we got a whole bunch of guys that did a whole lot of mass, which led us to our current model, which is the quantum model. And this is where things get a little fuzzy. And so we're going to write down the basics of what we have to know about the quantum model of the atom. And for the dates, you want to put 1924 through 1926. So it was a lot of exciting things that were going on in chemistry and physics at this point. And the three guys that we associate with the quantum model, not all, I mean, the thing to remember is that all of these guys led to, Democritus coined atom, Thomson found the electron, Rutherford found the nucleus, Bohr came up with quantized paths. So they all led to it. But the three guys we associate with the quantum model are de Broglie. Wow, having a little trouble spelling today. Let's try this again. Okay, R. de Broglie, Schrödinger. On a roll. All right. Okay, de Broglie, Schrödinger, S-C-H-R-O-D-I-N-G-E-R. De Broglie said, let's treat electrons like waves. Schrödinger did a whole lot of math that essentially his equation allowed us to support the idea of Bohr's quantized levels. And then we had Heisenberg, who said, okay, you cannot know the exact velocity and location of an electron at the same time. Now, if we think about the quantum model, this is where we started getting these whole 3D orbitals. So if we draw some orbitals on here, there's my nucleus right in the middle. Remember, the first orbital with the lowest energy level is the 1s, and it's spherical shape. So we draw a circle, kind of represents the sphere. Then the next one that you would have would be the 2s. Okay, there's another sphere that's just bigger. The 1s exists on the inside, but it's bigger. Now, we're also going to draw a set of 2p orbitals. So I'm going to have 3 dumbbells. I'm going to have 1, I'm going to have 2, I'm going to have 3. Okay, so these are my 2p. There's 3 of them. Sometimes they're referred to as 2px, 2py, and 2pz, but we're just going to say 2p. And for a description, what we need to make sure that we have on there is that the Schrödinger did a whole lot of math, but it still wasn't exact. All we can really state is that electrons have a high probability. So we did all that math, and we're still like, well, we're fairly certain they are. High probability of existing in 3D. So now we're 3D. Okay, we're kind of like balloons. Bohr, 2D, or bits. Okay. Quantum, 3D, what are called orbitals. And they can be anywhere in these orbitals. Okay, so if it's in this 2p orbital, the electron can be anywhere in there. Okay, 3D orbitals. Okay, and that's going to be the difference. So, on your test, it's going to say, describe the model, the development of the atomic model from Democritus to quantum. You have to include the dates, you have to include the people, the pictures, the descriptions. About the only thing that you don't have to include that's on this sheet is where we wrote the questions on Thomson. You can, but those questions were driving what the next thing. But everything else on this page, you need to make sure that you include. If you have any questions, ask me. And hopefully that was helpful in summarizing the development of the atomic